My name is Deniz Üner, and I'm a professor of chemical engineering at the Middle East Technical University.
Recording in progress.
Chemical Engineering Department at the Middle East Technical University is chosen by the Ministry of Development and endorsed by the Higher Education Council on the 11th day of June of this year as the National Coordination Center of Catalysis Research and Development between academia and industry. And it was a lucky coincidence that we were organizing this conference on behalf of the Catalysis Society of Turkey at the Middle East Technical University in collaboration with Samsun 19 Mayıs University. We intended to organize this conference between the dates of 19 and 21st of May 2020. It was expected to be hosted by Samsun 19 Mayıs University. We were planning to organize a catalysis conference and at the same time commemorate the inauguration of the independence movement under the leadership of Mustafa Kemal on May 19, 1990. Due to complications of COVID pandemic, we were stranded in our homes and we had to postpone our conference to a date that we couldn't settle upon. Eventually, we realized an online conference starting today until the 11th of September 2021. Today is also a precious day for Turkish independence. We are commemorating the victorious conclusion of the independence movement on September 9, 1922, and we remember all the members of the movement under the leadership of Mustafa Kemal Atatürk. Let me give you some brief timelines for Catalysis Society of Turkey. The society is formally established on November 26, 2005. So far, we have organized 8 conferences, all with international participation, 6 summer schools, numerous local and online activities. Last year, we have organized 8 Zoom conferences, which received participations between 100 to 250 participants. Our society is a member of FCAST, European Federation of Catalysis Societies. Our society is a member of IACS, International Association of Catalysis Societies. On this 8th conference of the Catalysis Society, we are going to have 3 plenary lectures. The first plenary lecture will be given by Professor Jeffrey A. Reimer. He is the department chair and then has an endowed chair at the Chemical Engineering, Chemical and Biomolecular Chemistry Department, Chemical and Biomolecular Engineering Department of University of California, Berkeley campus. And this will be our opening lecture. Tomorrow, Professor Johannes Lercher of Technical University of Munich and Pacific Northwest National Laboratory will deliver a belated François Gault lecture. François Gault lecture is a prestigious award lecture of the European Federation of Catalysis Societies. Professor Lercher was the speaker, former Gault lecturer, but he was unable to attend our conference organized in Adana. So he is going to participate in our online conference to give his lecture, to deliver his lecture. Professor Ümit Özkan from Ohio State University is going to deliver a lecture, a plenary lecture. This lecture will be a part of the special session we are organizing to honor Professor Gülşen Doğu and Professor Doğu and their contributions to the fields of catalysis and chemical reaction engineering. We're going to have 8 oral, 1 poster sessions. All of these conferences, all of these sessions will be organized online. You're going to experience this level of a conference organization first time. So technical difficulties are anticipated. We wish your patience and forgiveness and understanding during those technical difficulties. So before I turn over to start the regular program, I would like to express special thanks. First to Dr. Berker Fıçıçılar. He has been an instrumental member of the organizing committee. We have organized until the last month of the conference in 2020, and it was a last-minute cancellation. So we postponed this conference several times. He has been very patient with us, and his collaboration and cooperation is kindly and deeply appreciated. Professor Gürkan Karakaş has taken the torch very recently as the co-chair of the organizing committee. Professor Naime Aslı Sezgi has served as the chair of the program committee. The conference secretariat has been conducted by Ms. Canan Karaevaz and Merve Sarıyer. They will be with us for the technical part of the conference. We are grateful for their hard work and patience. Catalysis Society Executive Board and Catalysis Community Without Borders have made this conference possible. Other special thanks are due to Ankara Kent Konseyi. They will provide live broadcast of the plenary lectures from their YouTube channel with simultaneous translation to Turkish. I'm right now using the school principal's desk at St. Beyciğ Öğretim Okulu in Elazığ through Uzaynet Telecommunication Services. A little bit of commercial touch to my thanks. Thanks are also due to the members of the Catalysis Society who are with us right now and who contribute to the scientific part of our conference. So this, with this introduction, I will switch to Turkish and say a few words in Turkish. Bütün katılımcılara iyi akşamlar dileklerimi ve hoş geldiniz dileklerimi iletiyorum. Şu an yayınımız Ankara Kent Konseyi'nin YouTube kanalından da canlı olarak aktarılıyor. Ankara Kent Konseyi Çevre ve Sıfır Atık Çalışma Grubu ile yeni oluşturulmakta olan Ankara İklim ve Çevre Meclisi'nin özel gayretleriyle bu canlı yayın gerçekleşiyor. Kataliz alanı hem sıfır atık, hem çevre, hem de iklim değişikliği konularında çok değerli ve çok temel rol oynayan bir akademik alan. Bu konferansımızın konuşmalarının tamamına yakını bu alanlarda gerçekleşecek. Bu alanlarda yapılan ulusal ve uluslararası çalışmaları bu konferansta dinleyeceğiz. Tartışmalarımız bu alanda gerçekleşecek ve davetli konuşmacılarımızın yapacağı konuşmalarda yine çevreye, atıksız bir çevreye, iklim değişikliğine yol açan olayların en aza indirilmesine ve giderilmesine yönelik akademik çalışmaların tartışıldığı bir platform olacak konferansımız. Bu çerçevede Ankara Kent Konseyi'nin bize gösterdiği bu desteğe çok teşekkür ediyoruz. Bu konuda YouTube kanalından bizleri izleyen değerli katılımcılara çok teşekkür ediyoruz. Türkçe tanıtımımı burada tamamlayıp birkaç dakikalık bir aradan sonra Profesör Jeff Reimer'ın tanıtımına geçeceğim. Hepinize katıldığınız ve katılımınız için teşekkür ediyorum. Değerli katılımcılarımıza özellikle mikrofonlarını kapatmaları için bir hatırlatma yapıyorum. 5 dakika sonra görüşmek dileğiyle. Dear participants, we are going to take you to the waiting room briefly before we start our plenary lecture of Professor Jeff Reimer.
Right, test
Hello,
1, 2.
Professor Jeff.
Hi, how are you?
Fine, and you?
Good, thank you. Very good.
We are together with the Candan.
Yeah.
Maybe you want to share your screen?
Okay, let's see how that goes.
Uh-huh.
How does that look to you?
Good, very good. No
Can
problem.
you see my arrow?
Yes,
Yes, we can.
yes, we can see.
Good. Super.
Okay.
And is it warmer today in Ankara or not?
Daha normal. Evet,
A
hocam.
little bit.
Okay.
Hocam, we are taking the participants in the Zoom platform now. If you are ready.
What did I do?
We are taking the participants in the Zoom
So,
platform.
yes, yes, of course.
They are in the
Yes, of
waiting
course.
room.
Yes.
Okay. So
Now
what we're
we-
saying now, people don't hear.
I'm taking it.
Tamam.
And movie has some complex characters, so let me review the characters with you before we start the movie. On the left-hand side of the screen is a concentration of CO2 in the atmosphere as a function of position on the planet, the equator, North Pole, South Pole. This point in particular is important for you to notice. That's a CO2 monitoring station on the island of Hawaii in the Pacific Ocean. Over here is another graph in which we have also CO2 as a function, CO2, but now as a function of time. And in the middle is a map that shows the locations, the stations wherein CO2 is measured. And then there's a little clock running. So there's a lot going on. So let's go ahead and start the movie and take some observations as to what's happening with the planet. So first of all, we see in Hawaii, the CO2 concentration goes up and down, sort of oscillates. In the South Pole, it also oscillates, but much lower amplitude and out of phase with the northern part of the world. The baseline level of CO2 is clearly rising all over the world, and some stations appear to be much noisier than others. And you can see the stations popping up as a function of time here. What's clear to everyone, I'm sure, is the average rising increase in concentration of CO2 as a function of time. And we're getting close. I believe this graph, particular graph ends in 2015 or 2016. And right now, as of today, we're at about 414 parts per million. But right about 2015 or so is when the planet exceeds 403 parts per million. Let's go back in time, just to the Hawaii station, back to the early 1950s, see the oscillation and the decrease. Now we're going to use tree rings and ice cores to go back further in time. And we're looking now at a pre-industrial era. Let's go look at some more ice cores and go way back in time, thousands of years. And you'll see that it is true the CO2 concentration does oscillate with a very different frequency, and it goes up and down. Reminder that we are here today, and now this plot will go back to about 800,000 years before the current era. So the CO2 concentration in the atmosphere changes a lot in history. It's changed very differently in recent years. These are the countries and institutions that contributed to these data. Some of them are friendly to Turkey. Some of them are maybe less friendly to Turkey and or the United States. But it's just a reminder that collecting these data is an important mission for all of us in terms of understanding what is happening on our planet. So the question is, of course, why is the CO2 rising? The data obtained in Hawaii started with this man, Dave Keeling. The curve that I've shown here is called the Keeling curve, and it represents the concentrations in this Hawaiian island as a function of time. Now, the obvious hypothesis is that because we burn things, we're increasing the CO2 in the atmosphere. So if our engines are so responsible, there's a parallel part of stoichiometry that tells us, of course, we must be consuming CO2. And it was Dave's son, Ralph Keeling, who began in the 1990s a series of measurements and analyses that showed, yes, indeed, we are consuming oxygen, although because it's about 20%, measuring part per million changes is tricky, hence the O2 to N2 ratio. And one of Ralph Keeling's key contributions to the literature at that time was to recognize that the slope here is consistent with the stoichiometry, provided you take into account CO2 absorbed into the oceans and CO2 into the soils. So we are changing the atmosphere because we're putting CO2 from burning. So let's analyze that a little more quantitatively, and let's jump to the Jenswalde power station right at the German-Poland border. That particular power station is an engineering marvel of efficiency, and just a reminder that as of a few years ago, 1/4 of Germany's power still came from coal. I'm not currently aware of the fraction in Turkey, but worldwide coal represents a significant contribution to electric power production. So let's go to the Jenswalde power plant and ask how much CO2 comes from that plant. Well, this is an elementary stoichiometry calculation. It's a 3 gigawatt plant, and that gives us the energy consumption. This is the heating value of coal. This is the efficiency of the plant, and we can turn that into a certain mass of coal. That's about 25,000 tons a day. That's a lot of coal. So to picture that, I'm just showing you a picture that the Jenswalde power plant has about 218 railroad cars of coal delivered per day, 365 days out of the year. All right, well, let's see, that's coal. How about carbon? Well, we can do the stoichiometric calculation, and we discover that there's over 3,000 cubic meters per second of flue gas exiting this power plant. So that's a lot of gas. So how am I to imagine so much gas? Well, let's take an architectural landmark like this one, and we'll go to the diagrams and discover it's about 300,000 cubic meters. That means the Jenswalde power plant would fill the Trump Tower every 92 seconds with exhaust gas, and 12% of that is CO2, just from one coal-fired power plant. Let's take a step back and look at worldwide production just from coal. In 2017, 1,400 million tons of coal, of CO2 were emitted just by coal-fired power plants. That same year, the world produced 344 million tons of plastic. Or to put that in slightly differently, we put 4 times as much carbon into the atmosphere that year from coal alone than all the plastics produced. So the atmosphere is changing, and it's changing because we're using it as the receptacle for our carbon waste. So how does the Earth cope with this massive increase of CO2? And that's best viewed in what's called a variance spectrum, which is an interesting way to view this. This on the vertical axis is the change in CO2 concentration in the atmosphere on a log scale. And the x-axis is the time scale of a physical or chemical event that leads to that change. So you can see, looking at carbon, that there are daily events, yearly events, tens of to hundreds of thousands of years events, and million-year events. So what are the physical processes that contribute to those peaks? And for that matter, how does our perturbation to the atmosphere look on this diagram? Well, first of all, the daily one is easy. Plants take up CO2 during the day because of photosynthesis. So there's a change on a daily basis. On the annual cycle, remember what the Keeling curve had these little ups and downs in it? That represents the annual cycle. Let's blow up the Keeling curve and take a look at one region. Here is June to August in one particular year. In the summertime, the Northern Hemisphere takes up CO2 because the plants are growing and they're decaying and dying in the winter and increasing CO2. And you'll notice carefully in this curve that the start of the year and the end of the year have slightly different endpoints. That's about 3 parts per million. That's just what you and I have contributed during that year. So that's the annual cycle. And then we have this whole range of features that appear tens of thousands of years. So how do we measure that? The picture above shows ice cores. And I just want to let you know that the countries represented here are not necessarily friendly on a political scale. Scientists collaborate together, and you can imagine the following. As snow falls in, let's say, the Arctic or Antarctic, it entrains within it a sample of the atmosphere. And then the next year, another snowfall, and the next year, another snowfall. And over the years, a vertical ice core represents a frozen plug flow reactor in which we see changing CO2 concentrations. So it's these ice cores that allow us to go back in time and look at the concentration of CO2 in the atmosphere. And this is another vision of that changes in CO2 from about the beginning of the industrial area back in time, 800,000 years. And these peaks here represent these various cycles. A number of things contribute to them. Some we know and some we don't fully understand. Certainly the changing solar output, the change of orbit of the Earth around the sun, and so forth. But a key element appears to be associated with the circulation of the oceans. That is to say, warm surface currents take up CO2, either physically or biologically. They're subtended into cold flows, and then they reappear later on. And this time scale for this river of carbon to move from surface to underground back to the surface represents a bolus of CO2 with these kinds of time scales. Understanding the role oceans play and their circulations is one of the critical features of climate change that we need to understand further. Well, what about this really long time scale, the thing that happens over millions of years? For that, we have to look at a little bit of geochemistry. So I'm sure all of you understand that water and CO2 produce carbonic acid. Carbonic acid etches away the silicate rocks in the soil and deposits mineral elements and bicarbonate into the oceans. The minerals are taken up by plants and animals, and they're taken to the bottom of the ocean as calcium carbonate. And carbonate. And then, of course, what happens is plate tectonics subtend some of that carbonate to the deep earth where it's very hot, and the reverse reaction occurs, the silicates form, and CO2 reappears in the form of volcanism. So what's interesting about this large, massive geological timescale and cycle is the size of the reservoirs. So if I put the amount of carbon in the atmosphere equal to 1, then there's over 5 million times that amount of carbon in the deep earth, which is to say perturbations that happen up here are ultimately damped because this carbon change is equilibrated with a large reservoir 5 million times, the ocean 50 times, the near surface 100,000 times. So that represents the geological timescale. These are probably oceans and other events, yearly photosynthesis and daily. So the question is, where do we fit in? So here's that CO2 on this time scale. And now we have to expand the range of this to get today's value, which I have as 414 parts per million. So this change is our contribution to the Earth's variance spectrum. And here's a peak representing our contribution. That is to say, we have already perturbed the carbon cycle by a value at least as big as these other processes. So we are changing the atmosphere, and the Earth responds over many timescales. So the question is, what are the consequences of these changes in carbon content? The most obvious, and the one probably of concern to many of you on the Zoom today, is temperature. I like this graph, which I picked up from a Science magazine article, because it represents a variety of different sources, one of which was actually funded by climate deniers. And it shows the change of the global temperature over time. And as you probably know, 2020 and 2016 were the hottest recorded in history. And 2021 is certainly headed to be on that order. So how is it that we can understand that? Can we use simple thermodynamics to appreciate why changing CO2 in the atmosphere would lead to a rise in temperature? In its simplest form, this is an easy calculation to do. Undergraduates do it in our classes at Berkeley. So what you start with, sunshine, it's a black body radiating at about, 3,000 degrees C. And here's a black body radiating at about 10 degrees C or so. So these fluxes go into space. And you know, those fluxes are proportional to the temperature of the body. So we understand what thermal equilibrium means. That means the flux arriving on the Earth is matched by the flux of Earth into space. That's one of our fundamental paradigms of engineering science, right? So let's now imagine an experiment. Let's go into space and put a big umbrella and drop the flux of solar light from the sun onto the planet Earth. If we do that, the flux at the Earth goes down. And because of this equilibration, then the Earth shine into space also goes down. And because of the Stefan Boltzmann law, this tells us that the temperature of the Earth must go down. So this is a cartoon that represents an example of what we call geoengineering. That is massive infrastructure changes that would, for example, drop the temperature of the planet. So let's look at the Earth in a little more detail, because a lot of things are happening besides what's in that previous diagram. So here's a picture here that reminds us that the incoming light is partially reflected, and Earthshine makes up the difference in watts per square meter. So this represents equilibrium. But of course, a lot is going on down on the surface. We have condensation, evaporation, changes that are happening, cloud cover, albedo, and so forth. So a great deal is happening down here below. But let's imagine that now that rather than put an umbrella in front of the sun, we're going to take an umbrella and put it towards the Earth to block some of the Earth shine. That's what greenhouse gases do. Now, they don't block all the light that's emanating from the black body Earth. The clever thing and the subtlety about greenhouse gases, of course, is that they block a portion of the light emitted from the planet that isn't already absorbed by other gases on the planet, like water. So greenhouse gases are a window shade. And what does that mean? It means it drops the Earth shine. And when the Earth shine drops, we're out of equilibrium. And so radiative forcing is a concept that tells us that the Earth shine must change, and that is related to the temperature of the planet. And so in this particular case, when greenhouse gases drop the Earth shine by 0.6 watts per square meter, this imbalance leads the temperature of the planet to rise. Now, to be honest with you, until really just a few years ago, this was mathematically modeled and understood physically, but had anyone actually measured it? And the answer is a group of intrepid scientists figured this out. So they went into space. They use infrared cameras largely to look at incoming, reflected, and incoming sunshine, reflected sunshine, and outgoing Earth shine. And then down on the planet, they use cameras to look at how much sun arrives on the Earth and how much is reflected back from the various things. And then they measure changes in the greenhouse gases, and from that compared it to the radiative forcing. And this is a beautiful plot from this paper, really on December of 2015. So let's just take this in for a minute because I find it to be a very beautiful curve. This is the radiative forcing measured from those devices over a 12-year time span. Here's the measured change in CO2 concentration over that same time span. And the blue line represents the temperature change trend over that same time period. The fact that they match tells us that our CO2 waste is warming the planet by radiative forcing. I like this movie. I'm sure you've seen it before. It represents a snapshot or a movie of the planet temperature as a function of time because it's graphically so powerful and illustrates that where we are at now is very different than we've been in recorded history. And I want you to notice in particular how much warmer the Arctic is than the rest of the planet, or how much warmer it has become. So-called Arctic amplification has to do with the fact that when you change the amount of ice in the Arctic, then the surface albedo changes and warming ensues because ice reflects a lot of sunlight. So what are climate scientists to do? Well, they, of course, create mathematical models that predict conservation of mass, momentum, and energy on the planet. They grid the planet, do a massive calculation, and ask, how are we to figure out whether our models are correct? And the answer is you go back in time and you compare measured data to the calculated data back in time before you go forward in time. I like this animation very much because having done that, then the authors can look over the past 100 years and ask, how have other things contributed to the warming of the planet? So here, for example, represents the orbital changes for the sun during that time period and their contribution to radiative forcing. Here's the solar output, which we know varies a little bit. And let's see, what else do I have? Oh, yes, volcanic activity. Volcanoes like the Pinatubo one here introduce dust, which cools the planet. So these are all the natural forcing factors taken together, and that's the contribution to global warming during that period of time. Now let's take human factors, land use. We're digging up things and making changes to our forests all the time. We do emit ozone into the atmosphere. We have aerosols. As we said, aerosols cool the planet because they act as a sunshade. And then here's the greenhouse gases, mainly carbon dioxide and methane. And so now we can take the human factors together and add them up at the bottom of the graph, as shown here. And now we can take human and other natural factors all together. And the extent to which the red line matches the black line is the extent to which our mathematical models accurately connect temperature and radiative forcing. That's a pretty competent graph. So I know what you're asking. Thermodynamics says the planet is warming. Radiative forcing says it's warming. But what about just this last winter? And here's a picture taken from the US government that shows the temperature in February in 2021. And those of you who read the newspaper will remember there was a huge cold storm in particularly Texas at that time, power failures, extreme events. How is it possible that thermodynamics says the planet is warming, and yet we have these events that are clearly wildly cold? The answer goes into this intricate balance between thermodynamics and transport. So we're all aware of the various jet streams, the subtropical and the mid-latitude jet stream. These winds are derived from temperature differences between the pole of the planet and the mid-latitude. And of course, that temperature difference has been going down over time. As we said, in particular, the Arctic amplification is warming this part. And so it suggests that perhaps these winds are changing because the planet's temperature is changing. And indeed, in 2015, authors did some balloon and other measurements to get the kinetic energy of winds, the wind speed, and the thermal velocities, and they all showed a decrease in velocity. So the question then was, were these changes in atmospheric dynamics leading to these unusual winter weather events? So Arctic amplification, the polar vortex have appeared in the media quite extensively, but we really needed a connection between the two. Is this hypothesis correct, that we used to have a stable polar vortex, but some planetary warming has led to distortions of this? And this paper, which just came out last week, is an extraordinary contribution to the literature. These authors looked at data around the planet and particularly looked at the snow in October and the September sea ice. And the snow in October represented increased surface albedo over Eurasia. And this represented reduced ice because of warming, exceptional warming over the Barretts, which is near Alaska. So 30 years of data, and the authors compared that data to climate models, which included winds, and the extent to which the black dots overlap the extreme events in temperature is the high confidence points for these climate models. And this paper, which is a heavy read to be sure, basically says before climate change, we had a very stable situation in which there was an upward energy wave from eastern Siberia that had this nice balanced circular polar vortex, which kept the winters warmer, that is thermodynamically warm. But what has happened with this heating over the Barretts and this change in albedo over Eurasia is that this upward energy wave has moved north. It's distorted and stretched the polar vortex so that the jet stream now dips down during this month of February in the United States. That is to say, climate modeling and climate data have been combined together with transport phenomena to see this dynamic balance between thermodynamics and transport. Okay, so what are some of the other consequences? A very important one, sea level. So this paper was published in 2015 in which the authors made a very controversial claim, namely that historically the seas have been rising at a certain rate, but in more recent times that rate has been accelerating. Very controversial paper. So a different group of authors reanalyzed the data and came to the same conclusion. That is to say, the sea levels are rising, but they're accelerating in their rise. So how could that possibly be? Well, you have to look then at, for example, what happens with melting ice at Antarctic, at Greenland, and in the Arctic. And the Antarctic contribution alone represents an increase in the sea level. And why is that? Allow me to use simple pictures to say, that is to say, when the planet warms, warm water expands and that raises the sea level. But as ice melts, it fills the oceans. And so the acceleration represents warming water expanding and water being added to the ocean from our decreasing glaciers. That has interesting consequences. I'm going to re-show this thermohaline circulation, and you'll notice that some parts of the world experience ocean currents that are warm relative to other parts of the world. So let's take a look at this part of the planet, for example, and let's go to the data. Here, the data are from satellite altimetry, and these represent the changes in sea level on average. And here is that point I showed you previously on the map. It's a place where warm surface currents are at the surface, and it's a place where warming water is rising rapidly, and hence the Marshall Islands are disappearing. There is no small irony to the fact that the CO2 that you and I have dumped into the atmosphere are displacing the people in a faraway place who are, by and large, poor. So the Earth has seen this before. Let's go take a look at some of these data. And so now we're going to use analyses of shells buried in the oceans and go way back in time. So here we are over here. Let's go back, say, 70 million years. Here's the deep ocean temperature. And this is a proxy for this is the measurement. Oxygen reacts differently, O16 and O18, this isotope effect. So the ratio of O17 to O18 and O16 gives us a measure of temperature. So here we are, glacial periods, but what is this? What is this rise here? It's called the Paleocene-Eocene thermal maximum. And so what authors and scientists have done is they've analyzed seashells that are buried in the oceans, and they've looked at the isotopes of carbon and oxygen. Why carbon? Because the carbon-12, carbon-13 ratio is a proxy for where the carbon comes from and the CO2 comes from in the atmosphere. And there was a massive depletion about 55 million years ago of C13. That means a huge amount of CO2 and methane were introduced into the atmosphere at that time. So that's about 4,000 gigatons of carbon this represents. And right now, you and I have introduced just about a third of that. So here's the proxy for temperature. Here's the planet temperature. And you'll see that we have a rise of about 6 degrees C during that period of time. And by the way, there was so much CO2 in the oceans that the number of shells essentially vanished during that time because of the acidity of the oceans. So here was an experiment the planet Earth ran for us. It dumped this much carbon into the atmosphere. These are the consequences. And by the way, after a couple 100,000 years, we're back to where we were before. By the way, where did the carbon come from? A topic of some interest. This recent paper suggests that it was likely due to volcanic eruption. So here's the planet at the Paleocene-Eocene thermal maximum. Okay, I show this graph because it's shocking, and I confess to it. So let's just take a step back and remind ourselves that 55 million years ago, the continents were in different places because of continental drift. So the appearance of the planet looks different, of course, because of that. But I want to call your attention to two features. These are the temperatures around the planet, the average temperature day, night, year round. And just as a reminder, in the present era, the average temperature in Ankara is 11 degrees C. So there are portions of the planet in which it exceeds the wet bulb temperature that is sustainable for human life. Just about everywhere is a difficult place to live. And the other feature I wanted to call your attention to is that when there's very little ice left on the planet, the ocean sea level rises are immense, and certain portions of the world are very, very different than what they are today. So the atmosphere is changing. The change is due to combustion. Radiative forcing connects them. Sea levels rise as water warms and ice melts. The Earth has seen this before, and in 200,000 years, we're all back to normal. So what about some other consequences? Now I'm going to speed up a little and just dance through some of the physical consequences. For example, weather. This paper is an extraordinary one. Even though it is quite old now, it's still one of the most powerful ones for you and your students to examine. Jim Henson, famous climate scientist, now retired from NASA, posed the following question. Let's take some data. Let's go to Ankara and take the temperature from this window of time and make an array of points out of it, and then make a plot, and a bell curve for the temperatures during that period. And of course, there's going to be an average, and one expects that there will be rare events in which you're 2 or 3 sigma away from this average temperature. And so the question Hansen and his colleagues asked is, how much of the Earth has experienced a larger than 2 or 3 sigma event in recent times? So we'll take this average window and then map that onto a graph of the Earth to show how many extreme warm weather or cold weather events have happened. So red is a 2 sigma standard deviation, brown is 3 sigma from the average high. So here's the planet in 1955, some places warmer, some cooler, 1965, 1975. Are you ready? Here we are, 2011. That's when this paper, the last range of data that this paper took into account. And as you know, 2016 and 2020 were the warmest ever. This is intuitively obvious to many of you. If you take a bell curve or a typical statistical profile, if you change the mean a little bit, the tails change a lot. And this is exactly what Henson and his colleagues showed with these data. So glaciers, ice levels, ocean currents, let's run through these. Here's the Rhone Glacier in Switzerland. Here it is here in 2014. This is from the internet. I was actually there climbing around the glacier at that time. Here's an artist's painting, which you can get on a postcard in this Rhone Valley of the glacier in 1850. It's just a pictorial way to realize that glaciers are shrinking. We have a lot of data on glaciers. Look, these are thousands of glaciers, and this shows the changes in their front as a function of time. We can make a graph of that and look at the change in mass with respect to time. Yes, it is true a few glaciers are growing, but worldwide, all the glaciers are shrinking. And here's the plot for 30 famous glaciers. How about Arctic ice, the North Pole? Here's a nice little movie that shows you the sea ice extent at its minimum, that is at the peak summertime temperatures. And you can see how much the Arctic sea ice has diminished. You're probably aware that in your lifetime, we expect the Arctic ice to vanish. How about Greenland ice? A recent paper in which they looked at the ice mass with satellite data, and then they use optical and infrared imaging methods to look at how much water is flowing out of Greenland. And you can see the ice mass change. So Greenland is losing ice. Let's jump to the Antarctic. Each of these circles represents a place in the Antarctic. A blue represents mass gain in this window of time, and brown represents mass loss. So I'm going to show you three graphs superimposed. So here's 79 to 89. Here's the whole Antarctica, 89 to 99, 99 to 2009, 2009 to 2017. Antarctica is losing ice at a pretty dramatic rate. And yes, there are a few places where it is not so. So what about a threat to Turkish climate? Well, as you know, one of the key features of the Earth's planet is this current that comes up, warm surface currents that come past the Europe and subtend and come back down again, the so-called Atlantic meridional overturning circulation. And there was a paper published a couple of years ago in which the authors were suggesting this current might be changing. And the suggestion was based on a climate model, which showed that in some portions of this circulation, the temperature would be rising, in other portions it would be lowering, and the total amount of flow would be dropping. So this is based on mathematical models. So let's jump to a paper just earlier this year in which they looked at data. I won't go through the data exactly, but I'll just call your attention that every one of these proxies for the ocean circulation in this current are going down. So what this means then is the consequences for North America and Europe and perhaps worldwide are pretty extreme, which is to say, if the temperature rises in front of the Northeast, then coastal flooding will be much more rampant. And if the temperature drops and the flow rate drops over here, that means Europe will experience increased storms. All of these are true anecdotally to you as well. And finally, I'll just say that just last month, another paper appeared in which the authors actually used data and confirmed these proxies that indeed the flow rate is dramatically changing of this important circulating current. All these things are happening. And I haven't said anything about biology. And that would take well, another lifetime of research, but certainly another hour seminar to summarize. So other consequences I just want to mention in the last few minutes we have together, because this is a topic that's become very important to us all at this time, which is the difference in income between us and others has become more extreme. And has climate change contributed to that? Our colleague Marshall Burke at Stanford University looked at data about global warming, that is temperature data over time, such as I've shown you here, and asked what were the consequences for economies. Perhaps not surprising to you, cool countries benefit economically with warming, and warm countries experience cumulative losses with warming. And this leads us then to look at the probability of economic damage from climate change. And you can see the cool northern part of the northern hemisphere actually experiences less economic damage than the southern hemisphere. But as you can imagine, the consequences for the billions of people who live in these places is pretty extreme. Well, let's take some mathematical modeling and look at the 2 degrees C warming scenario. My colleague Solomon Chong here at UC Berkeley published this paper recently. Okay, 2 degrees C warming. So let's take a look at the planet in that scenario. So here is the surface temperature as a function of latitude. That is from the middle southern hemisphere to the middle northern hemisphere. This is the predicted surface temperature. And what the authors did is they took the slope of that and calculated then the temperature change as a function of latitude on the planet. And then they took the slope of the x-axis to get the gradient, that is the temperature change per degree change in latitude across the continents. And a negative number doesn't mean cooling. A negative number just means that the delta here was a negative number. So you can take those data and calculate a slightly different curve, which is how far would you have to move in order to keep the same average temperature that you're experiencing today. And what you see is there are portions of the planet in which the length scale at which you'd have to move is extraordinary. So here's a map the authors prepared for us that shows how far you'd have to move in miles, sorry, the US number, in miles to keep the same temperature. And you'll notice that there are portions of Turkey in which people would have to move a long distance in order to keep the same temperature. But just about everywhere on the planet, people have to move tens, hundreds, and maybe 1,000 miles to keep the same temperature. So here's the change in population density if people actually migrated to keep the same temperature. I'll just call your attention to this particular part of Turkey in which you have a 300% change in population. So there are enormous geopolitical consequences to the planetary temperature change. Let me summarize. We extract things from the planet. We extract coal to power our lives. We extract liquid petroleum to power our engines, and we extract natural gas to produce the things that make our lives good. Every one of us on this Zoom call today profits from these industries, either directly or indirectly. But there are consequences such as a warming planet. And these consequences are not shared equally. Some people visit the consequences much more extreme than others. And as it turns out, the poorest people of the world would seem to be experiencing them much more dramatically than the rich people of the world. And that's why I'm going to end this lecture today by asking you to join this mission of our planet to mitigate the effects of our carbon waste in the atmosphere. It's an important thing for us to do. And thank you very much for your attention this evening.
Thank you very much, Professor Reimer. It was an excellent talk, giving us basis of thinking further of what we are doing and what we should be doing. Professor Reimer can entertain a few questions if there are any.
Should we use the chat room for that, or do you open up the microphone?
Yeah, the chat board would be preferred.
Okay.
We don't seem to be having any questions. The facts are dramatic. The global warming and human activity on the climate change evidence is striking, and very recent data is doing very striking observations as well.
I see.
So
the race.
I don't see any questions coming.
Can I ask a question?
Deniz Hocam, Emre Hoca has a question actually.
Yes, please, Emre Hocam.
Thank you for the nice presentation. It was definitely interesting. This is Emre Hozensoy from Bilkent University, Ankara. I think we hosted you some years ago at Bilkent University as well.
I remember.
And so the quick question is, I mean, this is always something I wondered. So, you know, we just dig into the ice to get this CO2 information going back in time, right? So I was just wondering what, probably you're not, I'm not sure whether you're familiar with that, but what is the accuracy in these kind of measurements analytically? So, you know, like we're trying to estimate the CO2 levels in the atmosphere thousands or even billion years ago. I'm not really against global warming, don't get me wrong, but I was just wondering the accuracy of these measurements. So how accurate are these measurements? What are typical error bars in these measurements?
Yeah, so I know a little bit about this, Imra. I can't fully answer your question, but what I've read and use in my class is that the mass spectrometric data are, of course, very, very precise. That is, to be able to determine the isotopic ratios of various gases. The challenge comes in converting isotopic ratios into a number like concentration of CO2 in the atmosphere. And that I know is very challenging. I know each year I see a paper in which another sort of arcane isotope is examined to try and match the chemistry of that isotope with what is known. And so that's a big area in climate science, let's just say, atmospheric isotopic geochemistry. So the error bars are significant, but multiple measurements give the same results. So the accuracy is high, the precision is high, and the accuracy is less high. The trend lines are very clear. And I think if I were a geochemist, I would really be excited about working on connecting the isotopic data from my mass spec to what's going on in the ice cores. Maybe that didn't help, but it is very difficult to do.
Yeah, thank you. Thanks.
I had a connection problem. I'm going to ask on behalf of a participant, asking about the best strategies for the climate change in terms of novel carbon capture mechanisms, which is the research that you contribute quite enormously to the literature.
Well, I think that was a compliment. I'm going to take it as such. Thank you. So there's basically three strategies for mitigating carbon in the atmosphere. One is very familiar to all chemical engineers, which is absorption. That is, you take an exhaust gas or even air and bubble it through an amine solution to capture CO2 as a carbamate. And then you, in an absorption column, then with a stripping column, you remove the CO2 for compression and storage. That process works. You can buy it today. The problem with that process is that it's expensive and costly in terms of the power to run it. Nevertheless, it is commercially available, and there are pilot scale facilities that are using that technology. Another technology that also appears to be very promising is to use membranes. And those of you also trained in engineering, even water engineering, understand that large scale membranes are easy to make. And if you can push an exhaust gas or even air through them and somehow separate CO2 from nitrogen and the other gases, that works. It works on a pilot scale even, and there are companies pursuing that. And lastly, which is an area that I'm most involved in, which is adsorption. That is, we take the kinds of powders that we know are effective at differentially absorbing gases like CO2 versus nitrogen. And we have a powder-based process in which you have temperature or pressure swing to capture and then release CO2. The challenges with that technology is thermal management. That is, how do you heat and cool powders quickly? It's not so trivial to do. And also the chemistry of designing materials that are cheap, inexpensive, and fall into a circular economy that can be used for that. All three of those strategies are well past the lab scale now into pilot scale, and even in some cases on massive scales. So those are three good strategies. And the last thing I'll say about that in response to your question is that there is a parallel or companion community that's looking at utilization. That is, I take CO2 from the air or even from an exhaust stream, and even before separating it, utilize that CO2 for some product so that I defossilize the carbon economy. It's unlikely we're going to get rid of plastics and everything related to carbon in modern life. But if the source of that carbon is from CO2, then at least we've defossilized the production of those materials. So utilization and capture are the two main strategies. Sequestration is a whole nother talk, and I'll spare you all on that. But let's just say there's been enormous progress on what to do with CO2 and putting it underground. That looks very, very promising.
How about resource conservation, cutting down our consumption of fossil fuels? I mean, Trump Tower example that you have given was very striking, that every 92 seconds of a power plant uses a Trump Tower equivalent of coal and discharges corresponding carbon dioxide to the atmosphere. Maybe we should be a little bit more conservative in the way we consume energy.
The device efficiency community is an important one. Building efficiency is very important. Consumer consumption is important, although I'm dangerously close to political territory, and that always scares me a little bit. But what I might say is that the guilt an individual has about their personal consumption is, in my opinion, not an effective strategy for climate change. An effective strategy are laws, enforceable and planet-wide, that allow us to reduce our consumption in a systematic and thoughtful way. I'm fortunate to live in an area where I can choose to have 100% renewable energy for my home, all solar and wind. It costs maybe a few pennies a month more than it would be if I derived my home power from the traditional sources. Those are all good choices to make. The one thing you did mention, and I should have early on, which is what is a great new frontier for all of you scientists on the Zoom call today, which is the carbon economy of farming. Soils can absorb a great amount of carbon, and management of farms and management of soils turns out to be a really great pioneer place that has not received as much attention as it should. There are pilot scale studies around the world, particularly in the USA, that show that an enormous amount of atmospheric carbon could be sequestered with a modest change to our farming practices that are modest in cost and not difficult to implement. And so that's an area, Professor Uner, where things could change quickly with respect to our farms.
Thank you very much. I think we have run out of time. Professor Reimer is greeting the day while we are saying goodbye. This is just an evening time, and we should be moving along with our program. Professor Reimer, thank you very much for your time, for this excellent presentation, and I'm sure we will be watching again on our YouTube broadcast as well. Best wishes to California, but one last note about perhaps our carbon dioxide economy is that the way that we conducted this conference saved a lot of carbon dioxide, that we didn't fly you from California to Turkey. Neither one of us moved from our coordinates. We are now using very, very, very small amount of energy on our computers to realize this conference. It's just, we are losing the benefits of the personal conversation and personal touch, but as far as communicating the information, we are benefiting a lot to the carbon economy, so to say. Thank you very much, Professor Reimer, again. We have our silent applause for your presentation.
It's an honor to be with you. Thank you so much for hosting me, and you have a nice evening now. Goodbye.
Goodbye. We are going to have a 10 minutes of break, and we will be back at the hour to continue with our contributed talks. between Atılım University, Gazi University, and Niğde Ömer Halis Demir University. Dr. Doruklu is going to talk about an alternative method for ammonia synthesis by electrocatalysis using nitride conducting solid electrolytes. Dr. Do, Zoom platform is yours for the next 15 minutes.
Thank you very much. Thank you, Dr. Ner, and thank you everyone for joining. Wish we could do this in person, but this is better than nothing, I suppose. As Dr. Ner said, I will be talking about an alternative ammonia synthesis method today that we suggest, propose. And well, I probably shouldn't have to make this introduction in an audience like this, but ammonia is one of the most produced chemicals around the world, definitely among top 3, and it is used in many different industries. Fertilizers, of course, but besides that, many nitrogen-containing chemicals are produced by using ammonia. It's used in explosive industry, textiles, refrigeration, cleaning products, pharmaceuticals, energy, and recently there are studies on direct ammonia fuel cells because, well, when compared to hydrogen fuel cells, ammonia is easier to store and transport. It has good energy content, and even if you use hydrogen fuel cells, it can be used as a hydrogen carrier. And since it doesn't have carbon, it might be a feasible option. So it is increasing. The production of ammonia is increasing every day with introduction of these new technologies, new products, new industries. As you all probably know, it is currently produced by Haber-Bosch process, which requires high temperature and pressure. Especially high pressure is a serious concern, and it's a thermodynamically limited process. And there are also some pollution problems with Haber-Bosch process. When I first say this, people sometimes say, why is there a pollution problem? There's no carbon in it, nothing in it. So yes, there's no carbon in this reaction, that's correct, but the hydrogen that is supplied for this Haber-Bosch process is mostly produced by carbon gasification or some fossil fuels. So there's some carbon dioxide emission when the hydrogen is produced. As a result, so for the ammonia production also, we have some carbon dioxide emission. So this leads to researchers to check for alternative options, and it's very there are many researches done around this area. People are trying to find alternative production methods. Also, when I talked to industry, I had some industry meetings in the last 2 years, especially. One of the things that industry thinks about ammonia supply, so these are the industries that use ammonia for some production. One of the things they talk about is supply-demand chain or balance for ammonia is not really constant, and this leads to fluctuations in ammonia prices, and this is a concern for them. And another thing about ammonia is, well, there is this carbon tax issue. Well, it's not used right now, but soon we will be seeing it. And it doesn't matter if in Turkey we have this carbon tax or not. Probably in Europe, they are considering getting carbon tax for imported products that are not produced totally carbon-free. So if we are producing something using ammonia for it and exporting it, we have to prove that it is produced carbon-free, and ammonia is produced carbon-free as well. So because of these issues, many companies try to find methods to have an in-house ammonia synthesis facility so that they can produce the ammonia that they require for their production this way. And Haber-Bosch is not great for that because, first of all, the hydrogen is usually supplied with use of carbon or carbon fossil fuels. And another thing is Haber-Bosch process is efficient, economically efficient at very high quantities. So they're looking for lower quantity solutions because building a Haber-Bosch plant just for their production might not be very feasible for them. For that, among alternatives, there are many alternatives actually. There are many research going on in here. We think electrocatalytic route suggests a good option because first of all, it uses atmospheric pressures. That's a big advantage. Second is it has a simple reactor design. That's another advantage. It can produce ammonia constantly without interruption, etc. Because of these, we think electrocatalytic route might be feasible. Well, there are other researches going on as well, so there might be other options too, but that is what we believe. And there are mainly two. I like to divide the electrocatalytic process into two, high temperature and low temperature, although it can be divided into different categories. I like to divide it like this way for easy interpretation. We believe high temperature might be more feasible, although low temperature has a big advantage of, well, temperature is low. So the materials we use are doesn't have to withstand high temperatures, or it might be economically more feasible too because the temperature is lower, but there are kinetic problems at low temperatures. At high temperatures, reaction rates are higher. So we work on high temperature electrocatalysis for this. And I would like to first talk about how this electrocatalysis works without taking too much time from you. So this is a setup similar to a solid oxide fuel cell, and in electrocatalysis we have similar setups basically. In a fuel cell, normally we supply some oxygen on the cathode. That oxygen for a solid oxide fuel cell, this diagram is for a solid oxide fuel cell that utilizes an oxide conducting electrolyte. So oxygen is ionized on the cathode, travels through the oxygen ions travel through the electrolyte to meet with fuel, maybe hydrogen, and electrons travel from an outside circuit to generate electricity. In terms of electrocatalysis, well, what we try to do is we try to regulate the oxygen ion flow also. So we don't necessarily have to be in the fuel cell region. So we might have to apply higher current, or we can do electrolysis. We can use in electrolyzer mode. So we try to arrange the ion mobility, and we try to supply the ions to the reaction sites for that. So coming back to ammonia synthesis for using these types of electrolytes, there are a handful of papers using proton conducting electrolytes. On this one, we have a hydrogen source, water or hydrogen. It ionized to produce hydrogen ions. Hydrogen ions travel through a proton conducting electrolyte, meet with nitrogen there to produce ammonia. So this is a kind of new area. There are not many studies on this actually, but still developing, and in recent years actually the number of publications are increasing on this. So with this we can decrease the pressure, especially the temperature. We cannot really do much because if we go to lower temperatures, the ion conductivity decreases, reaction rates decreases, so it doesn't become too efficient. So we still work at pretty high temperatures. There is only one study using an oxide conducting electrolyte. In this one, water and nitrogen are sent to the cathodes in here. The water is electrolyzed, oxygen ions travel through to the other side, and the remaining hydrogen in here reacts with nitrogen to produce ammonia, basically. So this utilizes water, and if we can utilize water, that would be a big advantage for us. Well, these two both have very big advantages. They are very promising. They both work at atmospheric pressure, so that's a big plus for us. But the problem is, in both of these, The nitrogen to hydrogen reaction occurs on the same side where we break the nitrogen bonds. And as you know, breaking those nitrogen-nitrogen triple bonds is very energy intensive and is not very easy. And as a result, we might see hydrogen recombination instead of forming ammonia. So what we propose, what we suggest is nitride conducting electrolytes. In this one, if we can have a nitrogen nitride conducting electrolytes, nitrogen can be ionized, sent through the electrolyte to the other side, and there it can meet with hydrogen or water and react to form ammonia. This might increase the selectivity because we are supplying nitrogen ions directly to the site instead of trying to break those bonds there. So that is what we are trying to work on, but this requires both development of a nitride conducting electrolyte and a suitable catalyst for this. I'll try to explain these separately and briefly. For electrolyte material, there are several different options like tantalum oxynitrides. They have a kind of low thermal stability, especially when the nitrogen content increases or the stability decreases. That's a problem because we cannot produce stable cells. It's hard to sinter them. The second is mayonites. Again, when nitrided, they have electronic conductivity this time, which we don't prefer. We don't want electrolytes to conduct electrons. We don't want them to conduct only ions. On the other hand, we have zirconium nitrides with again, some disadvantages, but ones that we can work on because they have low stability with high oxygen partial pressures, but we won't be at high oxygen partial pressures in our reactor. Or if we have high nitrogen partial pressures, we might have too much nitridation, which causes conductive phase formation, but we think that is more manageable. So, on the electrolyte development, there are different options, but for nitridation of zirconium oxide, formation of zirconium oxynitrides, there is the electrochemical nitridation route that we work on, but we cannot, I won't be presenting data about it for today because we had some repeatability problems on those. There's also a powder zirconium oxynitride synthesis, and after that, tape casting to produce the electrolytes. So we try to work on this. We started with nitridation of heat-ray stabilized zirconia, which has cubic structure, but well, as you can see, we first tried to treat them with nitrogen at high temperatures for extended periods of time. That didn't work. So we thought maybe we should add some reducing gas in there. So we tried a mixture of hydrogen and nitrogen. Well, it still didn't work. Well, YST, heat-ray stabilized zirconia, from the name, as you can understand, it's a stable structure. Maybe we cannot really reduce or introduce nitrogen in there very much. So we decided to try with zirconium oxides. That didn't work pretty well for us either. Again, we couldn't do much reduction. We couldn't get the phases that we want. Well, we can do these if we use ammonia gas, but we are trying to stay away from using ammonia for this synthesis for safety purposes. But seems like we might have to. Then we tried carbothermal nitridation of zirconia. And this one, we mix zirconium oxide with carbon, and at high temperature, we treat with, again, nitrogen. This time, we have seen some reduction and zirconium nitride production formation. But the problem is zirconium nitride might introduce some electrical conductivity, so we would prefer to be somewhere in between, zirconium oxynitrides maybe. So this might still work, but forming zirconium oxynitrides would have been better for us. Seems like these methods don't work very well, so we will still be testing these carbothermal nitrided ones, but we might have to switch to ammonia nitridation with ammonia using ammoniolosis. We are working on a setup for that right now. Next to come with catalyst properties. the catalyst that we require for this needs to have ionic conductivity, electrical conductivity. It has to be stable under operating conditions. Porosity and thermal expansion coefficient should be suitable for us as well. While thinking about this, we thought about myanites. It was an option for us, but for electrolytes. It is normally oxide conductive, can be doped with metals and ions to tailor the properties. And when it's treated with ammonia, with the ammonialysis reaction to introduce nitrogen ions in it, it becomes nitrite conductive, and it becomes electrical conductive also. So these might be beneficial for us in terms of catalysis. And also it introduces some anions such as with that combined nitrogen and hydrogen. So these anions can also work well in terms of reaction as well. So for myanites, there are different synthesis methods. Most commonly, it is synthesized by solid-state synthesis, but sol-gel route seems to be more promising because it offers smaller particle size. We can have more homogeneous structures at lower temperatures. So we try to work on sol-gel synthesis. Well, before going into this graph, our first trials for myanite synthesis were epic failures, basically, because it seems like the parameters are extremely important for the synthesis. So we started playing around with some parameters. Seems like pH is an important parameter. Increasing pH from 0.5 to 2 changed the structure. We started seeing more myanite formation. Next is TGA. I will not explain in extreme detail, but with temperature is also important. It definitely, from this TGA, we can see that it has to be definitely above 950, but at those temperatures, we couldn't get homogeneous, nice myanite structures. We need at least 1100 degrees Celsius to get some good myanite structure. And as you can see, in 1100, we still have some impurity phases. At 1200, we were able to get rid of these impurities and get pure myanite structure. Also, we tried introducing iron in the structure because we know, we think by introducing iron, we might improve its catalytic activity. That's what we wanted to try. With this amount of iron doping, with aluminum to iron amount ratio 13:1, we see some extra phases besides myanite structure. This is not unexpected. In literature, iron doping is done in much lower quantities. We are trying to understand what level of doping we can make actually. So we are still continuing on how much we should dope with iron studies. So that brings us to testing. So first of all, we want to test our catalyst, myanite catalyst, with oxide conducting electrolytes because we think that they will be active in both nitride and oxide conducting media. So we use a setup like this. I don't have much time left, so I will be quick. So we have some cells on a tube, and on inside the tube, we supply water and nitrogen, and we will be applying current to these cells. And we have a potentiostat to do that. And with a mass spectrometer, we will be analyzing our output. For our nitride conducting electrolytes, we need a planar reactor structure because we need to have two compartments because we will be feeding nitrogen from one side and we should be analyzing output of the other side of the reactor cell. So we need a different design. So we will be using these metal plate designs in that one. We are using glass ceilings on both of the methods, and we are applying current and trying to get the reactions going. So we couldn't do the activity tests yet because of many different experimental system problems that we face. But for now, we are able to do some synthesis work. We are hoping to test this in near future. To conclude, there are we need some alternatives to Haber-Bosch. With the increased amount of ammonia needs around the world, we need some alternative methods. And electrocatalysis might be promising, a promising option. But for nitride conducting electrolytes, yes, we suggest this, but we couldn't prove it yet until now. Hopefully, for our next meeting, I will be able to present you that this is a very, very great option. This is another study that I don't want to take your time with. There's a poster on this, again, a catalyst for ammonia synthesis. Merve will be presenting on it in the poster session. I would like to thank you all. Thank you to the organization committee for letting us present our work here. Thank you everyone for coming and listening to us. We are collaborating with Gazi University and Nida University on this work. And I would like to thank Atılım University Metal Forming Center of Excellence too. We are doing our XRD studies and some experimental work there. This study is supported by TÜBİTAK BİDEP 2232 program. Also, the last slide I showed, the lanthanum ferrite, perovskite, it is supported by Atılım University Research Support Program. Thank you very much. If you have any questions, I will be happy to answer.
Thank you, Dr. Doğu. We have time perhaps for a very short question. And of course, audience can contribute their questions during the talk on the chat board, which we can verbalize to the speaker. So I see no hands rising. Dr. Doğu, we have gone a little bit over time, so I will pass the discussion to your poster presentation, perhaps.
Okay.
And I will invite the next speaker to the platform. Thank you, Dr.
Thank you very much.
Dr. Çağlar. Dr. Başar Çağlar is contributing from Izmir Institute of Technology on his research on electrooxidation of glycerol on monometallic and bimetallic catalysts containing porous carbon cloth electrodes in alkaline medium. Dr. Çağlar, platform is yours for the next 20 minutes.
Thank you very much, Professor Akif. It's a pleasure to present my work here in the National Kataliz Conference again. And I would like to thank the organizing committee for being me a part of this conference, and also for the I hope we will have a nice conference for the coming 2 days. In this talk, I will going to present you the electrooxidation of glycerol and monometallic and bimetallic catalysts, and of course we will use the porous carbon cloth as a transport medium, and we perform this experiment alkaline medium, and I will show you what kind of results we get. This is a quite recent study, and this is also quite a new field for me, and I changed a bit the field towards the electrocatalysis side. And this is the recent published work, and this I will try to give a summary of this work today. This is my outline. You will follow this program. We will start with the glycerol oxidation, the importance of this reaction for us, and I will also introduce you what kind of materials and equipment that you need for doing this kind of study, and I will present you the cyclic voltammetry and impedance spectrometry results to figure out the activity